Basically what it's going to boil down to is that when we write our differential equations from now on, we're typically used to seeing it like this. Nth derivative of x with respect to time. So this could be second derivative, n would be 2, so d squared x dt squared. What we're going to do from now on most of the time in this guy is we're going to write that as the following. Instead of writing this big fraction with the differentials everywhere, the differential notation, we're going to write it in operator notation, which is a capital D with the superscript m x. Now make sure you understand what's going on here. So what we have is, this is what we call differential notation from calculus. So we have fraction d mth x dt to the mth power. Well, we're going to rewrite it as, anytime we see a capital D, we know that it's dx dt, basically, or it's d dt, really, is what we're trying to say. The superscript tells us what derivative we're taking. The x is sitting out here, much like this x is sitting out here. You can kind of think of this guy as operating on x. This whole derivative, this mth derivative with respect to t, is operating on x here. That's what gives us the derivative of that guy. Well, this is operating, this mth derivative, capital D, is operating on x. It's just that it's simpler, since we're always dealing with differential equations, that if we just write a capital D down, we know it's a derivative with respect to our independent variable. In this case, we're going to assume it's a function of time, but really the independent variable, since these equations are all a function of one variable, could be whatever variable you want. Could be theta, could be gamma, whatever, it doesn't matter. But typically in this course I've been using with respect to time, but you could be doing with respect to whatever. So when you do a capital D, it's basically saying take the mth derivative with respect to whatever variable we've been working with of whatever follows. So as an example, just to kind of nail it down and make it concrete, if I wrote down the following. Everyone knows this is the second derivative of x with respect to time. But notice how you have to put these 2's everywhere. Ugly fraction bar, all this stuff, the little lowercase d's, hard to read. Well, if I were going to write it in operator notation, it would be d squared x. And it means exactly the same thing. The capital D means take a derivative. The with respect to time part is implied just because x is a function of time that we're dealing with. Capital D means d dt, basically. The squared means second derivative. And whatever follows, in this case it's x, is just like it is here. It's just sitting there and you're operating on x. So basically that's the way it works, and it's going to greatly simplify how we write our differential equations, and also some of the solution methods we use later. This notation is going to make it much easier. So as examples, okay, what if we had the differential equation in the old notation, 3 and then second derivative of x with respect to time minus t dx with respect to time is equal to t squared. Right, so this is a differential equation we've been used to seeing. 3 times the second derivative plus, minus t times first derivative is equal to the stuff on the right-hand side. Now, if I were going to write it in operator notation, it would be very simply 3d squared x minus t d x is equal to t squared. Make sure you understand this. The 3 is still here because it's there. The d squared means d dt, but second derivative. It doesn't mean square anything. I keep saying squared, but it's not squared. It's second derivative, okay? But the d squared here means second derivative of whatever follows. In this case, x follows. Minus t stays from front. This capital D by itself means dt of whatever follows. In this case is x, same as here. So this is a direct translation of this. It doesn't make the problem more complicated, doesn't make it different. It's just changing the way that we write it down. The right-hand side stays the same. Now there's one little tiny thing that I do want to tell you, is that most of the time the way you do it is you can kind of treat these guys as sort of like an equation. Well, it is an equation, it's a differential equation. But you can factor this expression much like an algebraic expression. For instance, if I wanted to factor out an x is common to both of these terms. Then the way I would do it would be 3d squared minus t times d, close parentheses, x would be on the outside, is equal to t squared. Make sure you understand that. X was common to both. Instead of pulling it out on the left-hand side, pull it out on the right-hand side. Everything else is basically the same as what we had before. The reason this is important And this way, by the way, is usually the way we write it like this. So this, I'm going to put a star by this. This is usually how you'll see it written in books and everything else, is the following. We basically have a set of derivatives here with functions of time out in front of them, right? And they're sitting here, and this is what we call our linear differential operator. It is a set of derivatives that once we operate on x, yields the solution. So we have a set of derivatives operating on a variable, or I should say not a variable, on a function x. And when we do that operation, we say that it's equal to t squared. This is our differential equation. So it's really important for you to understand that, because this guy is really the linear differential operator for this problem. So we're going to say that this is our linear differential operator. And we put it in quotes, L. Usually you write it as L. L means linear differential operator. So it's the same exact thing as what we had before. It's no different. We just wrap our derivatives together, have a slightly different notation, and we say that whatever's in parentheses operates on x. When we say operates, it's like if you want to actually do the math, then you would distribute this x back in and operate on x here. You would distribute it back in and operate on x here. Taking the derivatives, here you would take two derivatives of x. Here you would take one derivative of x, and you would recover this original differential equation you have. Now, I think you can all agree that something like this is much easier on the eyes than all these fractions and superscripts everywhere, especially if you have like a fourth order or a fifth order differential equation. Having it in this notation is going to make it a lot easier. And also, I'm giving a little bit of foreshadowing. When we get into solution techniques down the road, having it written like this is going to make it easier for you to know what to do. I'm not going to tell you why yet because it'll just get confusing, but just trust me on that. Okay, so let's write down in all of its glory what you'll typically see in a book. So in general, comma, a linear differential operator is written as follows. In general, you would write it as follows. L, we use it, the letter L, a sub n of t, d superscript n, plus dot, 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 a1 of t times d plus a naught of t. Okay, so this is the linear differential operator in the general form when you really think about it. Basically, the left-hand side of all these differential equations are going to have derivatives that decrease. So I have d sub n, I can have whatever I have in between. Eventually, I get to a first derivative and then no derivative. And out in front is just a function of time, a function of the independent variable. So it's exactly the same definition as when we talked about a linear differential equation, because the linear differential operator is really the same thing. It's just a different notation. So this is what you would see in a book. You look at that and you're like, oh my gosh, what does this mean? But it's just literally taking these derivatives that we had and sticking d's in their place and putting superscripts there to denote what level of derivative that we have. Okay? So in this particular case down here, we would say that the linear differential operator L is equal to 3d squared minus td. And that's it. And when you take this operator and operate on our function x, you get a differential equation. Set it equal to the right-hand side, there you go. This is getting into a little bit of theory that, theory of operators. You know, operator theory goes way beyond differential equations. Operator theory, you get into quite a bit into quantum mechanics later on when you have an operator operating on some function and you observe it and you see what happens there. So operator theory in this context is kind of growing your mathematical vocabulary a little bit. When you get farther down the road, you'll see how it ties into other branches of math, but this is sort of the beginnings of it, okay? So don't forget, though, that this linear operator L is really just a bunch of derivatives. Whatever it is I have for my differential equation, they're strung together. So for example, let me just give you a quick example. So for example, and actually I want to change colors a little bit here. Let's say that my linear differential operator L is equal to d cubed minus t d squared plus t cubed. And remember, when I say d cubed and d squared, I really don't mean take the derivative and cube it and take the derivative and square it. I mean third derivative and second derivative. It's a shorthand way of writing that, all right? So this is a linear differential operator, right? So what's going to happen there's a couple different ways to write this, but if I want to take this operator and operate on something, on some function, then the way I would write it is much like regular function notation from algebra. So I could take this operator L and I could operate on a function sine of 2t. Literally exactly like a function, f of x. So we have L of something. So if I'm going to do that, what I'm basically going to do is stick this function right next to each of these terms and operate accordingly. And so what I need to do is I need to figure out what the third derivative of this is, what the second derivative of this is, and of course this doesn't matter at all. So let's go ahead and do that over here. So if I want to take sine of, actually it's just probably easier just to do it down here. If I want to do sine of 2t, take the first derivative of it, what am I going to get? Derivative of sine is cosine, but I'm going to have a 2 out front from here. So 2 cosine 2t. Okay. Now, if I want to, let me stick with black for right now. If I want to take the second derivative, sine of 2t, second derivative, I need to take what I have and take the derivative again. So derivative of cosine is negative sine, so I'm going to have negative 2 times 2, because this 2 is going to come out, it's going to give me 4. Derivative of cosine is, like we said, negative sine, so we'll have sine of 2t. Right? So that's what we get there. And then if I want the third derivative, because I'm eventually going to need it, sine of 2t, third derivative, I just take the derivative of what I have again. Derivative of sine is positive cosine, so I have negative. 4 times 2 is going to give me 8 cosine 2t. So really all I'm doing here is calculating derivatives, because in order to operate on it, I'm going to need to do every single term. So what I'm going to need to do in the end, at the end of the day, just to write it all out, L of sine of 2t is going to be equal to, this is the differential operator, so I'm going to have d cubed operating on sine of 2t. And then I'm going to have minus t, this guy, d squared operating on sine of 2t. And then I'm going to have t cubed times sine of 2t. So all I've done is I've said, look, I'm going to take this differential operator and I'm going to operate on this function. So I'm going to have this guy operating on sine of 2t, which is going to be the same thing as basically having each individual part operating on the function, the derivatives. So I'm going to take the third derivative of this, I'm going to have minus t times the second derivative of this, and this is going to be by itself. Now I've already done the heavy lifting, so really what I'm going to have here is this guy's a third derivative, so negative 8 cosine 2t. This guy, the second derivative was given here, which was negative, but I have a negative here, so I'm going to have plus 4 times t sine of 2t. This is the second derivative. I stick it right here. I have a t here, 4 from there, negative times negative gives me positive. So I'm going to have plus 4t sine 2t, and then over here at the end, it's just going to stay the same, t cubed sine 2t. So L operating on sine 2x. So you're just going to get some practice here. A lot of differential equations books do this. They'll give you a linear differential operator and ask you, what happens when you operate on this function? What happens when you operate on that function? All you have to do is take the function and let each part of the guy operate on it, because like I told you before, it's kind of like distributing in, like we did here. This is my function. It's kind of like back distributing it to each term. So all you have to do is take the derivatives appropriately, and then everything else falls out. So when you operate this particular operator on this particular function, you get this. All right? Now, what I want to do here for just a few minutes is give you a few properties. These are the kind of things you read in books and you're like, what is he talking about? I don't even understand anything about this stuff, but really it's so simple when I tie it back to calculus. So one of the first properties you'll see is if you have a linear operator operating on two different functions inside. So this is like you're operating this operator on these guys, but really it's like the sum of two functions. Then what it's equivalent to is L operating on x1 plus L operating on x2. What this basically means is if I take two functions and as a group them together and then try to operate on them, it's the same thing as operating on each one of the functions separately. Each one of the functions separately. This is exactly the rule of derivatives that you've learned from Calculus 1. It just looks different because it's operator notation, but it's exactly the same thing. So let me tell you, this is ... like way back from Calculus 1. What do you get when you have d dt? So you want to take the derivative of two functions inside, t squared plus t. How do you take the derivative of this? Well, you take this derivative and you operate on the first one, and then you operate on the second one. So what you get is 2t plus 1. You have done this for so many years, you don't really realize what you're doing. It's kind of like you're taking this and you're sort of, quote, distributing it into this one and taking the derivative, and then you're kind of distributing over here to take that derivative. But basically what you've done is you've had a sum of two different functions on the inside, but it's the same thing as operating on each one of them separately, kind of like doing it like this. So it's the same exact thing. Let me give you another one you'll see typically in your books. If you have a linear differential operator operating on a function with a constant out in front of that function, then it's exactly the same thing as taking that constant out and then operating on that function by itself. So this could be a function of time. This could be a number 5 inside, right? The 5 comes out, and then you operate on what's left over, right? This is exactly the rule of derivatives, like d dt of 5t. How do you take the derivative of this guy? Well, you've been doing it for so long you may not realize it, but really what's happening is the 5 kind of comes out and you just end up operating on the t. So what you have is 5. The derivative of t is 1, so it kind of disappears and it just sort of stays the same. So really what you have is d dt of t. So the 5 comes out, you operate on this guy, leaving you with just simply 5, because the derivative of a t like that is just going to give you 1. So there may be other properties that you might see in your book, but I guess I'm trying to tell you that rest assured that all of them are things you already know. They just may look a little bit foreign, like new things, but really, because these linear differential operators are really just sets of derivatives added together, they follow all the rules of differentiation. So when you see sum rules and there's product rules, there's probably all kinds of rules you might see in your book, but they're all the same as the ones that you already know, because all of these L operators are things that you've already seen. They're just derivatives. So what I want to do next is do a couple of problems to give you a little bit more practice working with these linear differential operators. So what I'm going to give you in all of these problems is I'm going to give you a linear operator L, and I'm going to give you a function of time f of t. And what I want you to find is L operating on f of t. So there's two ways you can see it written in your book. One way I've shown you is when you have L parentheses with the function right here. That's pretty explicit, but you'll also see the function written right next to L without any parentheses around it. That means that L is operating on it. It's just two different ways of writing it. I know it's a lot of notation confusion a little bit, but if you see a function of x sitting next to that L operator, operate on it. That's what it means. So for the first problem, let's go ahead and get started by saying that L is equal to d squared minus 2d plus 1. And let's further say that f of t is equal to e to the t. So what we want to find, is L f of t. You might see it with parentheses around it. I'm trying to give you a broad understanding of the notation. So if you see an operator with a function next to it, it means operate on it, same as what we've been doing before. So really what you want to do is you want to operate this guy on the function, this guy on the function, and then this guy just sticks along for the ride. So let's go ahead and write all that out. So what we're going to have is L, which is going to be d squared minus 2d plus 1. This is L, sitting right next to e to the t. LF, right? And this was given by this. So what we're going to have is this guy operated on each one of these. So just to be totally explicit about it, I'll have d squared e to the t. Here I'll have minus 2d e to the t, and here I'll have plus e to the t. So it's like you're back distributing into each little guy, just kind of leaving it there. Now, when you see it written like this, you might know what to do, because you have second derivative of e to the t. Here you have first derivative of e to the t, and here you just have this guy right here. So to put it all together, LF of t, so you have this operator operating on this function, you'll have, so what's the second derivative of e to the t? Well, e to the t is indestructible, so it's just going to be e to the t minus 2, this derivative is e to the t, plus e to the t. So you have e to the t minus 2e to the t plus e to the t, which is 0. So really, in this particular case, the answer came out to 0. And that just happened to be the way the problem was played out, with the fact that negative and positive here. But mainly the most important thing is to know that when you operate like this, you have each part of your operator operating on your function. That's really the most important thing. So for the next problem, let's let L d squared minus 2d plus 1. Same operator, didn't really change that, but let's change the function and make it f of t is equal to 3e to the 2t, right? So what we're trying to find is LF of t. So you can write it out any way you want, but at the bottom line, at the end of the day, this function is going to need to be operated on by each part of this operator. So I'm going to need a second derivative, and I'm going to need a first derivative, so I'm just going to find it right here. F prime of t is equal to, here we have 3, and we have e to the 2t. The derivative of e to the 2t is 2 times e to the 2t. So 2 times 3 is 6e to the 2t. Just taking that derivative right there. Derivative of the exponent is 2 multiplied times this gives me the 6. Second derivative is just taking this, the derivative of this guy, same kind of thing. 2 times 6 is 12, e to the 2t. So it's indestructible, we just multiply because we're taking the derivative of the exponent there. All right, so what we're going to do next is write it all out in all of its glory so that you understand. What we're going to have is, operating, we'll have d squared minus 2d plus 1 operating on this function, 3e to the 2t. So when we do that, when we take this and operate with the second derivative operator, we get this, which was 12e to the 2t minus 2 from this times this first derivative operating on it is going to give us this. So I'm going to have 6e to the 2t. Make sure you understand my operator is not just the derivative by itself. It's d squared minus 2 times d. So I have to keep the 2 times the d that I've operated on here, 2 times 6. So I'm going to do that here in just a minute. And then plus this, just this 1, which is going to be 3e to the 2t. Draw a little divider here. So at the end of the day, I'm going to have 12e to the 2t minus 12e to the 2t plus 3e to the 2t. These guys are going to cancel because it's negative and positive. And so at the end of the day, I will have 3e to the 2t, which is the final answer. So if you just take the guy, take this operator, operate on a simple function, then when it all reduces down, this is what you're going to get. I'm going to do one more problem. Let's change the operator. Let me change colors a little bit too. We'll change the operator a little bit so that it's L is equal to d squared plus 3d minus 3. So that's our new linear differential operator. And then over here, we're going to operate on t cubed, right? So we're going to operate on t cubed. So just to make it a little bit clearer, we'll have L operating on t cubed, which is going to be equal to this operator we just wrote down, d squared plus 3d minus 3 operating on t cubed. So t cubed is just going to sit out there. You're going to end up distributing out. So I know I'm going to need a second derivative, and I know I'm going to need a first derivative of that function. So let's just go ahead and handle that right now. The first derivative, very easy, 3t squared. And the second derivative, again, very easy, 6t. So now we'll just slap it in there. And so when we do that, when we operate on this guy, taking the second derivative, we'll get 6t. But when we get to this guy, we have to take 3 multiplied by the first derivative, which is 3t squared, minus 3t cubed. Okay, so we've got everything operated on. Now we just have to simplify a little bit. So we'll have t cubed is equal to 6t plus 3 times 3 is 9t squared minus 3t cubed. So we have 6t plus 9t squared minus 3t cubed, and that's the final answer. So basically, this operator stuff, I just wanted to give you a little bit of a feel for it. So it's really just a shorthand way of writing derivatives. Notice that this doesn't really look like any sort of derivative that you've seen before in calculus, and if I set this equal to some function, it certainly would not look like a differential equation. So I wanted to split the section out so that you get your hands wrapped around these differential operators. Just know that they're a linear combination of derivatives, so they're going to obey all of the rules of differentiation. If you see something in parentheses, well, that's going to be your differential operator. It's going to operate on whatever function that you sit out of here, see on the outside of here. And so it literally operates term by term. You operate on this guy, operate on this guy, operate on this guy, exactly in the rules of differentiation. So as a foreshadowing, if I have a linear differential operator, I might write it as Lx is equal to, whatever sine of t. This is my forcing function on the right-hand side. This L is maybe some derivatives that I've kind of defined as a linear differential operator operating on x, which is the function I have. So this is the way that we're going to end up writing differential equations down the road. Don't forget that L is just a string of derivatives. It's just a shorthand way of writing a string of derivatives. It helps you keep your paper straight, so you should embrace it. And later on, I don't want to give too much away because it'll get a little confusing, but later on when we use some solution techniques, some certain techniques, writing it this way is going to actually help you get to the answer faster than keeping track of all the other stuff. And once you get used to the operator notation, you'll go through the rest of your course using it, and you won't even really think about differential equations in terms of writing all the superscripts everywhere. It's just going to be so much nicer and so much easier. So embrace it. Make sure you understand what it is. Don't gloss over it because you're going to be using it pretty much in every section from here on out. I'm Jason. I hope you've learned something here. Practice this guy. Get ready to get into some more solution techniques. Learning about linear differential operators is essential to understanding all of the techniques to follow. Learn anything at mathandscience.com.